And now we just finish what we started in the previous part, and we talk about the effective mass approximation. Now you saw how energy bands evolved, how we got energy bands, how we define valence band, how we define conduction band, energy gaps, how we distinguish between different solids, being them metals, insulators, or semiconductors. Now, this is what we discussed is the solid isolated from everything else. So we just considered one electron in a periodic potential, which is the solid, and there is nothing else surrounding this solid. So the solid is completely isolated from all the surroundings. Okay, and we got the band scheme. Now, in reality, and in engineering, and in electrical engineering in particular, we're going to use a solid and maybe apply electric field or potential, maybe optical excitation, maybe a magnetic field. And we're going to have not one electron, as I told you, we're going to have 10 to 22, 10 to 23 electrons per cubic centimeter. So we have a huge undertaking. External forces, meaning electric fields or magnetic field or optical excitation, these are all external that we apply. And then internal forces, we have all these electrons that are interacting with one another. So now, if we want to look at the dynamics, how things happen in a solid, then it becomes really difficult. Because if we want to abandon quantum mechanics, which is somewhat more difficult than Newton mechanics, classical mechanics, however, it's more appropriate. There are situations that Newton mechanics or classical mechanics can work very well and can give us a lot of information. So we can actually use it. But we have to take into account all these forces, external forces and internal forces coming from a huge number of electrons and a huge number of cores. So let us say that a total force, F, on an electron in a solid, realistically, comes from two parts. An internal force, F internal, and an external force, F external. And if we're going to use classical mechanics or Newtonian mechanics, just to make things simple, this total force should be equal to the mass of the electron times the acceleration of the electron. So what I'm telling you guys, I'm giving you a break. I'm not going to use the difficult quantum mechanics. I'm going to apply classical mechanics approximation. Okay, now what you're going to do is you're going to write 10 to 22 forces, internal forces, from all the electrons and all the cores. So you have 10 to 22 terms in your force equation. And then you have only perhaps one term coming from the external force. I'm talking about the force on one single electron. This force on one single electron comes from the external electric field, which is the Coulombic force maybe, or maybe comes from a magnetic force, maybe Lorentz force, or it may come from optical excitation, electron colliding with a photon. That's one external force. But then there are 10 to 22 internal forces which you have to add up. And these 10 to 22 forces come from the cores and come from the other electrons per cubic centimeter. Okay? So this term here, the internal forces, is a huge term. How can I get rid of it? Now, people thought about doing a trick. these 10 to 22 forces, maybe use a little bit of experiments, ignore them, which are the internal forces, and only use the external force, provided you use a special trick. This special trick is what we call the effective mass. So you use a different mass than the actual mass of the electron. And you call this mass the effective mass. And this mass, which is m star, which is the effective mass of the electron, takes care of all the internal forces. So the effect of all these internal forces is lumped into this effective mass. And then the equation becomes only one force, which is the external force, equals the effective mass of the electron times the acceleration of the electron. And therefore it becomes really simple. Now, what we have done here is we abandoned quantum mechanics, thank quantum mechanics for giving us bands. Thanks a lot. So that's what we need from quantum mechanics. Now, if we're going to put some signal, external signal to this solid, we are going to use the band scheme from quantum mechanics. But now we're going to use classical mechanics or Newtonian mechanics to see how the electron moves. So how can we use classical mechanics? We have somehow to ignore these internal forces, but we cannot ignore them. So what can we do? We have to work with the mass, effective mass, that takes care of all these effects. Okay? So let me bring that, bring that to your maybe perception with some kind of an example. Imagine you were walking in a classroom or walking just in the corridor. You feel the mass of your body. You can feel it. You can feel how heavy, how massful you are, how much mass you have. Now, if you go and try to swim in the sea, in the Mediterranean Sea or in the Red Sea, then when you are inside, when you are immersed, when you are deep in the sea water, you feel that you have a different mass. You feel probably that you're a little bit heavier, right? Or maybe even lighter. You feel a little bit lighter. So that feeling of the mass, lighter or heavier, comes from the fact that there are molecules and atoms in the seawater that interact with your body and exert forces on your body. Okay? And you can ignore the effect of all these forces by thinking that your mass is lighter or your mass is heavier. Same thing. If I take any one of you and put him inside an oil tank immersed in oil, you will feel a different mass. Okay? So, and if you're put in a different liquid, you'll feel a different mass. So, depending on the liquid, depending on the environment, depending on the internal forces, there is a different mass that you feel, which we will call the effective mass. Okay? How do we find this effective mass? We just have to use it in classical mechanics and then do an experiment and work backward, evaluate this effective mass from the results of the experiment. This is how they do it. However, in theory, the energy of the electron, now all the internal forces are blamed on the mass or are lumped in the mass. So the total energy is all kinetic. H bar k squared, which is the momentum squared, divided by 2m star, which is the effective mass. Now, I'm lumping all the effect of the internal forces on this effective mass. There are no external forces applied yet. So I'm just working with the energy of the electron in a crystal. So all the forces, internal forces, are not existent. They are all in the mass. So all the energy is kinetic. So E is equal to h bar k squared over 2m star, which is the momentum b squared over 2m star. So if I differentiate with respect to k, dE by dk, which would be h squared k over m star, and this would be h times p, because p, the momentum, is always equal to h bar k. Okay, that is the momentum, okay, using the wave nature of particles. So if I use that in this derivative, then I get h bar p over m star. And that gives me p is m star v, right? P is mass times p is momentum. P is mass, which I'm now going to use mass m star, effective mass, times velocity. So the velocity of an electron in a crystal is equal to 1 over h bar dE by dk. That is using P equals mv. And differentiating twice, again, if I go and get d squared d by dk squared, I get an expression 1 over m star is equal to 1 over h bar squared d squared e by dk squared. So if I know the energy form in k, if I differentiate it twice and divide by h bar squared, I get the reciprocal of the effective mass. So that's how I can get the effective mass analytically. I can also get it from experiments. Okay, so that's the trick. Once I have the effective mass, then I can apply it and use it in classical mechanics. So again, going back to the problem we had before, that is the semiconductor with this E versus K, that's the energy. Find an expression for the velocity of this electron in the conduction band as a function of K. And that is very simple. I just have to go back and apply this equation. This is V, which I just need to take dE by dk and divide it by h bar. And this is exactly what you do here. If you take the derivative dE by dk, the cosine becomes sine, as you see here. And it's 2.8. The derivative of 2.8 is 0. So V 1 over h bar dE by dk becomes 1 over h bar 1.7 a sine ka. Now, if you substitute, okay, what are for the values of a and the values of h, what you get this expression for the velocity as a function of k centimeter per second, for k in centimeter minus 1. So the velocity of the electron is 5 times 10 to 5 sine 2 times 10 to minus 8 k centimeters per second. And then the second question, what are the numerical values of this velocity at k equals 0 and k equals pi by 2a? So you just have to substitute k equals 0 and then k equals pi by 2a. And let's do that. If we put k equals 0, then sine 0 is 0 and the velocity is equal to 0. So at k equals 0, the velocity is 0. When we put k equals pi by 2a, then we substitute for k pi by 2a, this is a here, and we get the velocity equals to 5.2 times 10 to 5 centimeter per second. Then the next question is find the effective mass of the conduction band electron. So again, we go back and apply this equation here for the effective mass for that band. So what we do is we take the second derivative, 1 over m star, 1 over h bar squared, d squared e by dk squared, and that brings us back to cosine ka. And so we substitute, okay, for the cosine, okay, for k equals 0, the cosine of 0 is 1, okay, so the m star, let me see here, m star is equal to cos. So the m star equals sec, actually, sec 2 times, because the reciprocal of cosine is sec, right? So m star is equal to 6.37 sec this, right? So when we put k equals 0, sec of k equals 0 is actually 1. Okay, so maybe this is wrong. Okay, this is wrong. So it's not, m star is not 0. Actually, m star is equal to 6.37. Okay, so mass, that's in joule. Okay, so because the sec of a 0 is equal to 1. Okay, when we put k equals pi by 2a, sec pi by a is infinite. Okay, so we get for the mass, when k equals 2 pi, pi by 2a, m star is infinite. So we get an infinite mass. Okay, so that way we can analytically get the mass, the effective mass for the electron at any value for k. Okay, and what's the meaning of the mass of the electron is infinite? Meaning at that particular k, the mass of the electron is so heavy, the electron can hardly move. Literally what we're saying, this mass is so huge, nothing can move it. Or the electron, literally physically saying the electron is not moving when k is equal to pi by 2a. Okay, so that is what we literally mean. So that's this example, and this is concludes the energy bands in solid, just qualitative as well as quantitative approach, how to approach this. So that is, I'm going to stop